So in the previous classes we discussed about different kinds of differential equations, and today we are going to see how these differential equations are going to help us in solving some mechanics problems, right? So the heading is the differential equations in mechanics, right? So here is the first problem. So Manoj, can you hear me? Okay then. So let's start. This is the first problem we are going to encounter, that a particle of mass m is thrown with initial speed v0 inside a medium. A particle of mass m is thrown with initial speed v0 inside a medium, and a resistive force of magnitude minus kV acts on the particle. So find the distance traveled by the particle in some arbitrary time t, right? And k, there is the constant k is of appropriate dimensions, right? So that this will be of dimension of force. So there is a resistive force is acting on the particle. So initially the speed of the particle in the medium was v naught, is v0 or v naught or v0. Then when it started traveling in this medium, there was a resistive force or frictional force acted on the particle. And what is the magnitude of this frictional force? It is kb, right? It is proportional to its velocity. If the particle's velocity increases, then then the frictional force acting on the particle will also increase, right? That is the meaning of this resistive force. Such type of forces are also known as the viscous force, right? In fluids, if there is motion, then the viscous force or drag force that acts on the particle is proportional to the velocity of the particle. You may learn about them in the 11th class. The viscous force or drag force in a medium is proportional to the velocity of the particle in the medium, right? So here also there is a resistive force in the medium which is proportional to the velocity of the particle. So that's why this is the situation here. So let's suppose at some time t, this is the velocity of the particle v, and then what will be the drag force or the resistive force acting on the particle? It is just kv, right? So this is the drag force or resistive force acting on the particle in the medium, right? Is it okay, or is there any doubt from the question? Okay, then let's apply Newton's law here, Newton's second law. So here, what is the force? The only force acting on the particle is minus kV. Why minus? Because it is in the opposite direction of the motion, right? So that is why there is a minus here. The motion of the particle is in this direction, and the force is acting in the opposite direction, as this is a frictional force. So that will try to make the particle stop, as this is a frictional force. That's why it is acting on the opposite direction, right? So this is the Newton's equation, that force is minus kV acting on the particle. So what is force? Force is mass into acceleration, and acceleration can be written as dv by dt. And so here is the minus kV. So here I can write this as dv by dt equals to minus k by m into v. So this is a differential equation, right? So how to solve this differential equation? To solve it, we can use the variable separation method, right? The first method we discussed in the differential equation chapter is the variable separation method. So here you can take this v here, you can take to this side, then this will become dv by v, and this will become minus km dt. And now if you integrate it from the initial velocity was v0, and now the velocity is v, and the initial time was 0, and now the time is t. So now if you integrate this both sides, the integration of dv by v is ln v, and now apply the limits, and this side it is minus km t after applying the limits 0 to t. So this will become ln v minus ln v0, and this is here minus km by t. So this can be written as ln v by v0, or v by v0 is e to the power minus kt by m. So what is v? So v is v0 e to the power minus kt by m. So this is the solution for v, right, from this differential equation, right? Is it okay? That is, we got the v now, the velocity we got, but we know that velocity is dx by dt, or the derivative of the position with respect to time, right? So as v can be written as dx by dt, and we know what is v. V is here. So still then we can also solve for x. So what is x as a function of time? So in this way you can write that dx integration 0 to x. So dx is there. Take this dt to this side and integrate it from 0 to x, and time from 0 to t. So now if you integrate it, it will become x, and on this side if you integrate with respect to time, it will be minus mv0 by k, and the apply limit here. So this will be the x, right? So if you now apply the limits, it will be minus kt by m, e to the power minus kt by m, and e to the power 0 is 1. So here it is minus of 1. So this is position with respect to time, and this is velocity with respect to time, right? So we got how the velocity changes with respect to time, and we also got how the position changes with respect to time, right? So that was the question, right? The question was to find the distance traveled by the particle in time t. So the distance traveled by the particle in time t is this, right? Is it okay? Okay. Okay, so let me say it again. So there is, so let me give you a summary that there is a particle of mass m which was moving in a medium with initial speed was v0 or v0. The initial speed was v0, but there was a resistive force that was acting on the particle which is proportional to the velocity of the particle. This was minus kb, right? So here this was the particle, and here it is moving with velocity v at some time t, and there is the frictional force that is acting on the particle, or the resistive force that is acting on the particle in the opposite direction. So now if you apply the Newton's law, that F equals to minus of kV, right? Or ma equals to minus kV from Newton's law. So here this is the Newton's law, and acceleration A can be written as dv by dt. So here this is the differential equation you need to solve, and this can be solved by the variable separation method. And here we solved it. This is just an easy one, and so this is the velocity we got. Then after getting the velocity, we have to also find the position with respect to time. So here we can write velocity as dx by dt. Now if you solve this differential equation, the dx is here, and take dt to this side and integrate it from 0 to x, and here from 0 to t, just easy integration, and then you get the position of the particle as a function of time also. right? So we got velocity and position of the particle with respect to time. Is it okay? And so these are the plots. This is the plot for velocity. That velocity is just decaying with respect to time. So how was velocity? Velocity was v0 is sorry v is velocity v0. V0 is the initial velocity. e to the power minus e to the power minus kt by m. And here, what is position? X is mv0 by k multiplied by 1 minus e to the power minus kt by m. So these are the plots for velocity. This is the plot for velocity. Here you can see that velocity, due to the frictional force or the drag force or the resistive force, it is decreasing with time, right? It was, suppose this v0 is 1, the initial velocity was 1, and I take this k by m as 5. So let's just assume some values. Then if the velocity was 1 in the beginning, then it will eventually it will become 0 as time increases due to the frictional force. The friction will try to stop it from moving. So that's why as time increases, the velocity will just go to 0, right? Is it okay? Now let's see the position, right? The position is initially increasing, but as time increases, the velocity becomes 0 and the position of the particle remains stationary, right? So initially it is increasing, but as velocity becomes 0, the position becomes constant, right? So here, yeah. So here this is the velocity. As time increases, this velocity is decreasing. So at infinite time, this will just become 0, and this is position. And if you plot this function, you see as velocity becomes 0, this position becomes constant. Right here, this is becoming constant. Right, initially it was increasing, but now after some time it will become constant here. As v becomes 0, it stops moving, right? So that's why the position becomes constant. Is it okay, Manoj? Oh, it's okay, it's fine. So did you get this point? The velocity and position graph. Okay. So this was the first case. We got the velocity and position of a particle in a resistive medium, right? So here is the second case. The second case is about free fall. So here a particle of mass m is dropped near Earth, right? So you go up to a building and just drop a ball of mass m from the top of that building. So in addition to the gravity, there is a drag force proportional to the velocity of the particle that acts on the particle, and it is magnitude is gamma v. So find the speed after time t. Right. So this is the case where you drop a ball from a height, and when the ball falls due to gravity, but there is another force in the medium, that is gamma v, right? a resistive force is there in the medium, right? And this, what is the resistive force? It is gamma V. So the ball will, this is the initial configuration at the top of the building, suppose. So this is V0 and T is 0 and X is 0. So but after time T, the velocity is V and it is at position X. So here this ball will fall due to gravity, but there is another force acting on the ball, that is a resistive force or a drag force, due to, suppose there is a air resistance. Due to this air resistance, there is a force that is proportional to the velocity of the particle, and the proportionality constant is here gamma, right? So the gamma V force is acting as a resistive force for this air medium, and this is the situation here, right? Is it okay? Did you get the question? What is the question? Okay. So there is, so you will learn in the 11th class, the 12th class, that the ball will fall due to gravity, but here there is another force, the air resistance. We often neglect the air resistance in the medium. So, but here we are considering the air resistance. We are not ignoring it. So here, so what will happen? So here, if you apply the Newton's law, Newton's second law, that force will now becomes the gravity force minus of this drag force or the resistive force. This is the resistive force. This is also acting on the particle. So this is the now equation of motion, and here if you divide this gamma, this m throughout this equation, this will be the linear differential equation we have to solve, right? So how to solve this linear differential equation of first order? So first you need to find what is the integrating factor. I have mentioned this before in the class of linear differential equations. So you have to find the integrating factor. So how to find the integrating factor? So if this is the form of the linear differential equation is dy by dx plus pxy equals to qx, then what is the integrating factor? The integrating factor is e to the power px dx. This is the integrating factor. So here, what will be the integrating factor? What is px? Px is just gamma by m, and qx is just g, right? So here this is gamma by m dt, and what will be the integrating factor? This will be e to the power gamma t by n. Then what will be the solution? The solution will be v into the integrating factor, right? So as usual way to solve a linear differential equation of first order, that v into the integrating factor equals to q of x into the integrating factor, and then you have to integrate from 0 to t, right? So that is how to solve it. Now if you integrate this right hand side, so this will be the solution, and you get v as a function of time, right? So this is the solution of the this differential equation, right? Is it okay? Right. So this is the differential equation, and this is the solution. Now if you plot this v here, this is the diagram. So as you can see, initially this v is increasing, but after some time it is becoming constant. Can you say why this v is increasing, but after some time it is becoming constant, right? So if there was only the gravity force, then it will just increase forever, right? until it hits the ground, the velocity should be increasing forever if there is only the gravity force. But here there is another force, this frictional force is present here, and due to that, this is becoming constant after some time. If there is only gravity force or there is no friction, then this velocity will just increase forever, right? But here in this case, it is becoming constant. Can you say why the system is behaving in this way? Why the velocity is becoming constant? Hmm. Hello. So can you guess? So why this velocity is becoming constant after some time? Uh, so what if there was no frictional force? Then what will be the velocity with respect to time? It will just increase forever, right? So if there was, so let me show you that if there was no frictional force, then what will be the differential equation? There will be m dv by dt or mg, and mm will cancel out, and v will be just gt, right? So this velocity will just increase forever, right? If there was no frictional force or if there was no resistive force in this medium, right? But here this velocity is becoming constant after some time. Why so? Yes. Okay, let me tell you. So at this point, what is happening is that the point at which the velocity is becoming constant, what is happening? That is, this drag force is actually becoming equal to the gravity force, right? So then what will happen? The net force on the system will become zero, right? So that means acceleration is zero, right? Then what is this meaning? Then dv by dt is zero. Then what is the meaning? That v is constant, right? Is it okay, Manoj? So as this drag force is not a constant force, this gravity is a constant force, m into g. M is constant, g is constant, but this drag force is not a constant force. It is changing with velocity, right? Kb. So that's why after some time when this gravity is equal to the drag force, then the net force acting on the system will become zero, and at that point that means the acceleration is zero, or dv by dt is 0, then what is the meaning? Then that means v is a constant. So that's why this is v is becoming a constant now. So at the velocity at which the gravity becomes equal to the drag force, or become equal to the gamma v, that velocity is known as the terminal velocity. This is important. So so in exams, in entrance exams, they ask you to find the terminal velocity of the system. So you need to find when the gravity will become equal to the drag force or any kind of resistive force that is present in the system, then that velocity will be known as the terminal velocity. So this Vt is actually mg by gamma. This constant here, this coefficient present here is actually Vt, or the terminal velocity. This terminal velocity can also be found by taking t equals to infinite. So if you take here t is infinite, then you can also find what is the terminal velocity. So the terminal velocity is the constant velocity that appears when t becomes infinite, time becomes infinite, or gravity becomes equals to the drag force. This is the velocity of the particle with respect to time, right? So this is the solution to this problem. Is that okay, or is there a doubt? Hello. Is there a doubt from this problem? Okay then. So that completes this part. And today, now we are also going to discuss something about oscillations. So this will be not a detailed one, just how to solve the differential equations that occurs in the oscillation theory, right? So we'll just review the differential equations and how to solve them using our knowledge we gained in the previous 2 or 3 classes, right? So what is a simple harmonic oscillator? So a particle is said to execute the simple harmonic motion if the restoring force acting on the particle is directly proportional to the displacement and has direction opposite to the displacement, right? So a particle, so let me read it again, that a particle is said to execute simple harmonic motion if the restoring force acting on the particle is directly proportional to the displacement and has direction opposite to the displacement, right? So if there is a mass system here in this case here, right? So here is a mass and this is the spring and this is now in the rest position. Now if you stretch the string or just pull the mass here, then the string will stretch, or the spring, this is the spring mass system, right? Spring mass system. Now if you pull this spring in this direction, then the spring will stretch and the mass will displace. If the displacement of the mass is x, then what will be the spring force or the resistive force that is acting on this spring? It is kx, right? So if this is the force acting on the particle, then the particle is said to be executing the simple harmonic motion. That is, force is proportional to just minus of x. And what is a non-harmonic? If the force is proportional to x square or x cube, these are known as the non-harmonic systems, right? These are known as the non-harmonic systems. So the such systems are also known as the non-linear system, and the study of such systems is a subject itself. This is known as the non-linear dynamics, known as non known as the non-linear dynamics. So that is a subject in itself, like mechanics or classical mechanics. This is a subject itself. So in this subject, we study the non-harmonic systems or the non-linear systems. So here we are also just going to discuss about the harmonic oscillation problem, where the force is proportional to x only, or the displacement only, and it is not proportional to x square or x cube, etc. Right? So this is known as the simple harmonic motion. So what will be the equation of motion for this? Here, what is the force acting? The spring force. This is known as the spring force. The spring force acting on the mass m here is just minus of kx, minus k into displacement of the mass, right? This, what is this x? This x is the displacement of the mass from its equilibrium position, right? This is in equilibrium now. Equilibrium position, right? Or equilibrium configuration. Now if you disturb it or stretch the spring, then it will just displace it from the origin or the equilibrium position, and it will execute the simple harmonic motion, right? So this is the spring force, and this is the equation of motion from Newton's law, right? So how to solve this? How to solve this? So this is a differential equation, right? Because this ma plus kx equals to 0. This is a differential equation, and what is a? A is dv by dt, or this is a second order differential equation, and we learned how to solve them, the second order differential equations. So this is the second order differential equation we want to solve, and if you take here this m to this side here, so and if you take this k by m as some constant omega square, then this will be the differential equation of the simple harmonic motion, right? So here this can be written as d square plus omega square acting on x, right? What is d square? Here this d square is the second derivative operator, right, with respect to time, and this is just omega square, right? Now what will be the auxiliary equation? The auxiliary equation will be m square plus omega square, right? The auxiliary equation will be m square plus omega square, right? Then what are the roots? These are the roots of this auxiliary equation, right? Plus minus I omega. Then what is the solution? Solution will be a cos omega t plus b sin omega t. This is from the case 3, right? When the roots are complex but different, or the roots are complex conjugate of each other, then this will be the solution of the differential equation, right? This is the differential equation, and this is its solution, right? Is it okay? Yeah. Then now let's take these a and b are constants, right? This a and this b are constants. So now let's take this a as x0 sine phi and this b as x0 cos phi. So let's suppose this is the case. Then you can write this as x0 sine phi, put a as x0 sine phi and b as x0 cos phi, and this is nothing but sine of omega t plus phi, right? What is the formula for sine A plus plus B? Sine A plus B formula is sine A into cos B plus cos A into sine B, right? So by applying that simple trigonometric formula, you get the position of the particle with respect to time as this x0 sine omega t plus phi. This phi is known as the phase angle, and this x0 is the amplitude of the oscillation, right? And what is omega? Omega is the frequency of the oscillation, and this is the form you learnt in the 11th class, right? If you go through notes from the 11th class, this is the form they taught us. They just write it directly. This is the position of the particle with respect to time, and this phi is known as the phase of the particle, right? Right. So this is the x is the x0 is the amplitude of the oscillation. Omega is the frequency of oscillation. So and omega is just k by m root over, as you have taken omega square as k by m, and this omega is 2 pi f, right? So this omega is actually the angular frequency of the oscillation, and f is actually the frequency of the oscillation. So we just ignore that angular term. So somehow we take this omega as just the frequency of the oscillation. So we just write omega as the frequency of the oscillation, but omega is actually the angular frequency of the oscillation, right? And omega is just 2 pi f, and f is the actually the frequency of the oscillation. So here from x you can also find what is the kinetic energy and the potential energy of the particle, right? Because 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 kinetic energy because the kinetic energy is half mv square, and what is potential energy of the system? It is half kx square. You may learn it in the 11th class that kinetic energy is half mv square and potential energy for the system is half kx square for the spring mass system, right? So you know what is x, you know. Then you can also find what is v by taking the derivative with respect to time. V is dx by dt. So from this you can also find the kinetic energy and the potential energy of the system, right? So this is all about the simple harmonic oscillator and this differential equation and how to solve this differential equation, right? Using the methods we learned in the previous classes. This is the differential equation, this is the auxiliary equation. These are the roots, and applying case 3, the roots are when the roots are complex conjugate of each other. This is the solution, and using some trick you can also find the position of the particle with respect to time, right? Is it okay, or is there a doubt from this section? Okay then. So the next case we are going to discuss is the damped harmonic oscillator, right? What is a damped harmonic oscillator? In the damped harmonic oscillator, there is a resistive force present in the system. What is this resistive force? So if this mass is executing SHM on this ground, there may be a resistive force or a friction or a frictional force acting on this mass due to its contact with the ground, right? If this is the ground, there may be a resistive force. So here, this is the drag force or the resistive force is present in the system. And here we have also taken this resistive force is proportional to the velocity of the particle. So this resistance or this resistive force is also kind of a viscous force. That is the particles and the objects that experience in a medium, right? All the viscous forces are proportional to the velocity of the particle, right? So there is the concept is that the main concept is that the viscous force that V is actually proportional to minus CV or CV square, right? So this term when the velocity is for low velocities, but this term also so for those low velocities we ignore the CV square term, but for higher velocities we may consider the CV square term also. So this is the viscous force for any medium. So usually we ignore this term and we just consider this proportional to the velocity term, right? This is the concept. So here this is also proportional to the velocity of the particle that is executing the oscillation, and the proportionality constant here is beta, right? In the previous section, the proportionality constant was k in the first problem, but here this proportionality constant is beta. So what is the force acting on the system now? The force acting on the system is now the spring force, also the drag force, right? So there are two forces now acting on the system. So what will be the difference? What will be the differential equation now? The force is now here plus kx plus beta v equals to 0. Or this force can be written as mass into acceleration. And what is this? What is this x double dot? This x double dot is nothing but right. And what is x dot? X dot is just dx by dt. So this is the differential equation you need to solve, right? Now this is the differential equation you need to solve due to this drag force that is present in the system now. So this drag force is trying to stop the oscillation, right? We'll try to solve to stop this oscillation, right? So let's see how the system behaves when there is a drag force or a resisting force is present in the oscillating system, right? Is it okay? Or is there a doubt? Okay. So this is the equation of motion. Here there is an extra term present here from the simple harmonic motion. There was no term like this in the simple harmonic motion, right? But here, due to this frictional force or the drag force, there is a term like this here. That is proportional to the velocity of the particle. So this is the differential equation you need to solve. And so what we can write that here this is what is this d square is what is d. So here this is the differential equation you need to solve. So how to proceed? So first you have to find what is the auxiliary equation. Auxiliary equation is the place of d put m. So m square plus gamma m plus omega square equals to 0. And what is m? M can be found from the quadratic equation formula that minus b plus minus b square minus 4ac by 2a. What is a here? A here is 1. What is b? B is gamma. And what is c? C is omega square. So put everything here in the formula, and these are the roots you get, right? These are the roots of the auxiliary equation, right? Is it okay? Now how to find the solution? So these are the roots. So consider several cases. The case one is the case of light damping. But the damping is very small. That is why this gamma or the damping constant, this gamma is also known as the damping constant, which is proportionality constant for the drag force. This damping constant is much smaller than omega. From the much smaller than this frequency, the natural frequency of oscillation omega. That's why gamma square by 4 is much less than omega square, right? So this is the case of the light damping. The damping is very small, right? So when the damping is very small, the gamma square by 4 is much less than omega square. You can write this as omega square minus gamma square by 4 and take the minus outside, and the root over of minus I is I, right? This is greater than gamma square by 4, just exchange the terms, that omega square minus gamma square by 4, minus is still there. So here you write it as I omega square gamma square by 4, right? So if you write in this fashion, then this will be gamma by 2. So this m will now be minus, just minus gamma by 2 plus minus I omega dash. And what is omega dash? Omega dash is omega square minus gamma square by 4 root over, right? This omega square is, this omega dash is this term here, right? So what will be the solution? So if these are the roots, then apply case 3, and these are the solution, right? Is it okay? This is the solution, right? For this root, right? From which formula this solution came? Can you tell me? Hello? From which formula this solution came? If this is the root, yes. So do you remember the formula? What is the formula? If the roots are m is m1 plus minus I m2, then what is the solution? Uh, yes, very good. This was the solution, and we applied this method here. So what is m1 here? This m1 here is minus gamma by 2, and what is, yes, and what is m2? M2 is omega dash. So this is the root, and here we solved the case for the light damping. So let's see. Now if you take this a as x0 sin phi, as this a and b are just constants. So let's take a as x0, some constant x0 sin phi, and b as x0 cos phi. So if you put this solution, this a and b values here, then what you will get? You will get this x0 will be there, and e to the power minus gamma t by 2 will be there, and this is just sine omega dash t plus phi, right? So from the case of simple harmonic motion, how this is different? This was the solution for the simple harmonic motion, but here there is just another term here. This is the extra term that is appearing in the solution for the damped harmonic oscillator, right? In the simple harmonic motion, this term was not there. right? This extra term is appearing, and what is this extra term doing? The role of this term is to reduce the amplitude with time, right? So this is the solution, right? So initially it will start oscillating, but as time increases due to the friction force, due to the resistance or the resistive force, the amplitude will just go on decreasing, and finally it will become zero, right? So this is the term that is causing that decay like this in the amplitude, right? So initially this was the amplitude x0, but as time increases, this will just the amplitude will just decay or reduce like this way, right? So the resistance or the resistive force or the drag force is is forcing the particle to stop, right? To stop executing oscillatory motion, right? So that is the role of this term here, right? These are very important equations, right? These equations appear everywhere. Every damped oscillatory problem, such equations you can find that the amplitude will just go on decreasing, right? This is the solution of the equation when there is light damping or the damping is bit small, that is smaller than the natural frequency omega square, right? Is it okay or is there a doubt? Is there any doubt? Mhm. Okay then. So this was the case of light damping. Now let's discuss about heavy damping. When this gamma is much greater than omega square, that means the damping force is much greater than the spring force. What will happen? So here, this will be the case. And these roots, what are these roots? These roots are irrational type, right? So go through your root, the go through your notes that you'll see the last case we discussed about the when the roots are irrational type, and here there will be no t. So the irrational type roots. So these are the kind of solution we get, right? These are the kinds of solution we get for the irrational type root, and for this case, the particle will just if there will be no oscillatory motion, the particle will just stop executing oscillatory motion, and this kind of system are known as the aperiodic or the over damped system, right? There is kind of check the formula. What are the formula? There will be two. Yeah, so this will be the form of the solution you will get, and here there will be no oscillation, and the particle will just go to the equilibrium without executing any kind of oscillatory motion. If you displace it, it will just go back to the origin very slowly, right? This is the case of heavy damping. And the similar case is known as the critical damping. The critical damping is the case where this gamma square by 4 equals to omega square. They are same. Then this whole thing will vanish and the m will only be minus gamma by 2. That's why what will be the solution? The solution will be c e to the power minus gamma t by 2, and this will be the plot, right? Again, this is non-oscillatory. There will be no oscillation. If you displace the particle from its equilibrium position, it will just go back to the origin, right? Go back to its original position, right? This is the case known as the critical damping. Is it okay, or is there doubt? Okay, then. So these are the three cases known as the light damping or the heavy damping, and the third one is the critical damping. Now the third case we are going to discuss is the damped driven harmonic oscillator or the forced oscillator. Right? There is a external force also we are applying here. The equation is same. There is spring force, there is a drag force or a resistive force, but here there is an applied force that you are applying to the system. A time varying force that you are applying also, right? So here this is the kind of time varying force you are applying to the system, right? So in the previous places, what you are doing that if there is this is the system and this is the mass. So what you are doing, just give it a push and leave it and see how it is behaving, right? So just initially just give it a push, then leave it and you will see how this is executing oscillation, right? But here you are constantly applying a force to this mass. Extra force you are applying to this mass, right? So you are pushing or pulling this mass constantly. You are not leaving it there, right? So what will happen in that case? That is why this is known as the forced oscillation. You are forcing the oscillation, right? So if there is damping, then after some time this will just stop executing oscillation. But here in this case, you are not letting it to decay out. You are forcing the oscillation. So what will be the situation here in this case? In the case of forced oscillations, let's see. So there is an applied time varying force on the system. You are applying it. So the equation of motion will now become this one. This one was the original equation of motion from the previous case of damped harmonic oscillator. But here there is nothing. There is not zero here. There is this external force that is present here, right? That was zero in the previous case. This was zero in the previous case, but here this is not zero. Here you have an external force acting on the system. This is known as the damped driven harmonic oscillator. So what will be the effect? This is the force that is acting on the system. Then the complementary force. So this is a non-homogeneous type differential equation, right? This is a non-homogeneous type differential equation because this is not zero, right? For this differential equation, this second order differential equation. So here you have to find the complementary function and the particular function, right? So how to solve the complementary function? To solve the complementary function, you have to just take the homogeneous part and solve it. So for the light damping, so consider the damping is very low. So for the light damping, this will be the solution. This is known as the complementary function. and this is the particular function you have to also find. Then how to find the particular function? Now this is the f of d, and what is the particular function? Particular function will be this non-homogeneous part divided by f of d, and in the place of now d square, what you have to put? If the non-homogeneous part is sin x or cos x, what was the rule? That in the place of d square you have to put minus of a square, right? So here in the place of d square I am putting minus of omega a square, right? And these are the terms that is remaining also. So here these are the terms. Now how to solve it? Again there is a d here also. So multiply this term and this term in the both numerator and the denominator, right? So if you now multiply them, so this will be the denominator, and in the numerator you have to apply this operator, and if you apply it, so this will be the solution. So this is the particular integral, and you have also have the complementary function here, right? So this is the particular integral, and that is the complementary solution. So the net solution will be xc plus xp, right? So this is the solution. Is it okay, or is there any doubt from this differential equation? Okay then. So let me tell you that this solution of the complementary function in the language of oscillations, this is also known as the transient transient state solution, and this particular function is known as the steady state solution, known as the steady state solution, right? So this is known as the transient state solution, the complementary function, and this is known as the steady state solution. So why this is known as the transient, and why this is steady? So what happens that when you start start forcing the particle, or you start applying the force on the particle. So initially what will happen? This term will dominate, this solution will dominate. So the oscillation will start, and eventually it will die out. Then after some time when it die out, so this term will dominate after some time. So initially it will be like, initially it will start oscillating like this, it will die out, and then after some time it will just go like this. So this is the, so what is this part? This part is the steady state solution, and the complementary part, the xc, was this part. This was the transient state solution. So initially the xc will dominate, but that xc will die out with time. Then this xp will dominate, and this xp, that's why known as the steady state solution, right? So that is why these are named as the transient state solution, and this is known as the steady state solution. Is it okay, or is there a doubt? Okay then, Manoj. Is there any doubt from this section? Why this is transient, why steady state, and the solution of the differential equation? Did you get it or everything? Right. This is a, this is an example of the non-homogeneous differential equation that appears in physics, and the rest of them are examples of second order type differential equations that we can solve using your knowledge of differential equations that you learned in the previous 2 or 3 classes. So this is all about some the oscillation problems, and these are some mechanics problems that we encounter in daily life. Although these oscillations are not very detailed, so this the oscillation can be a chapter itself. But here I am just focusing on the difference of the three differential equations and how to solve them. And also there is one more thing. In the forced oscillations, there is something known as the resonance. So what is this resonance? The resonance is when, yes, so when this omega will become equal to omega a, right? So at that time, this amplitude, this xp will increase severely, right? So as there is this term here in the denominator, it is decreasing the amplitude, but as this will vanish, the amplitude will suddenly increase, right? And this omega equals to omega a when the applied frequency, this omega is known as the applied frequency, will be equal to the natural frequency. Omega is k by n root over. When this applied frequency becomes equal to the natural frequency of the system, then that state is known as the resonance state of the system. It is known as the resonance state of the system. For any kind of system, if the applying frequency is becoming equal to the natural frequency of the system, then that state will be known as the resonance state of the system. So that is the concept of resonance, right? So this is everything about today's class. So is there any doubt from this class? Okay. Manoj, is there any doubt? Let me stop recording, but the class is not over because I want to show you something. So is my screen visible now? So here, let's see some mathematical simulations based on this simple harmonic oscillation and damped harmonic oscillation and the forced harmonic oscillation. Not responding. Yes, now it is there. Enable dynamics. So is it visible? So here this is a simulation in Mathematica. So let's just see the simple harmonic oscillation. To see just the simple harmonic oscillator, let's set this initial position of the particle to 1, suppose 1 meter, and the spring constant is 9 here. You can see here, right? The spring constant is 9, right? You can see my cursor, right? And now let's take this friction to 0. The damping friction is 0, right? And what is mass? Mass is suppose 1. The force amplitude, let's take it to 0. There is nothing, just simple harmonic oscillation, right? So now let's run it. Here this is the simple harmonic oscillation of a spring mass system, right? And this is here the differential equation you can see, right? This x double dash is the double derivative with respect to time, and this is the spring constant 9, and x is there. So this is the simple harmonic oscillator differential equation, and this is the position time graph, right? The position time graph is just type cos omega t or sin omega t, right? We found the solution, right? Only type of cos omega t or sin omega t. There is no extra term, right? So that is how the sin omega t or cos omega t graph looks like. Is it okay? Manoj? Hello, Manoj. Hello. Maybe there is a network problem. So this is the simple harmonic oscillation. Now let's see the damped harmonic oscillation. So here you just need to change the damping friction here. So let's change the damping friction. Let's stop it. Let's take the damping friction something like this, right? Okay, this is the damping friction. So let's reset and run. So here see that this is oscillating, oscillating. The amplitude is decreasing. Yes. Now now it's stopped, right? Right? Yes. So here you can also see in this graph here, right? So here, so let me run it again. So here you can see the particle is following this graph, right? We also solved it for the light damping case. Here the damping is very low, and this decrease in amplitude due to that e to the power minus gamma t by 2 term, right? This e to the power minus gamma t by 2 term is actually reducing the amplitude of the system, and and after some time it is finally becoming coming to rest, right? This is the forced harmonic oscillator. Sorry, the damped harmonic oscillator, right? So now let's discuss the third case, that is the damped driven harmonic oscillator. That there is the damping friction is there, but here there is also a force. There is an external force. So let's apply a forcing amplitude. The forcing amplitude and there is a forcing frequency. So let me show you that. Yes, this is the perfect case. You see that. So this is reset and play. See what is happening. This is the case of forced, forced and damped harmonic oscillation. Just, just observe what is happening, and look at this graph here also. So from this diagram, can you tell me? So where is steady state and where is transient state? So this part, the initial part, all these crazy curves, these are the from here to here. These are the transient state, and from here this nice sine type curve. These are the steady state, right? So this the nice curve you are seeing here. This is actually the particular solution, and the crazy curve you are seeing here. It is decreasing with also with respect to time, right? This is kind of damped harmonic oscillator, right? So this is the complementary function. What is that complementary function? That complementary function is actually kind of damped harmonic oscillator. So initially the amplitude was there, but it's decreasing with time. So this part, after this crazy part is over, the transient part is over. The particle is going to the steady state. The nice oscillations are happening. So let me reset. So here, this crazy part is happening. The transient state is happening. Now the amplitude is decreasing, decreasing. Again, now the force, the external force is dominating the system here. Now this is the external force is dominating, and it is kind of oscillating with the frequency of the applied force. Right? This is the force driven harmonic oscillator. Right? And also see here near the forcing frequency when it is near 3, the amplitude is kind of very large, right? So why it is so? Because what is the natural frequency here? The natural frequency is k by m. So what is spring constant k here? It is 9. And what is mass? Mass is 1. So what is the natural frequency? It is k by m root over. So 9 root over or 3. So the natural frequency is 3. And what is the applied frequency? The applied frequency is here close to 3, right? So here you can see due to this equality, there is a kind of increase in the amplitude in the oscillation amplitude, right? So this is the state. This is not exactly the state of the resonance, but the system is near resonance. Because if I put 3 here, the the system will stop here because it will encounter an infinite a large diverge in this amplitude or the position. This is designed in that this simulation is designed in that way. But here this is close to resonance, So as you can see, the close to resonance, this the position is kind of very large. So here if I can just adjust here, this is so show you that, right. So as it is going near 3, the amplitude is increasing, right? And if you go back from 3, go back more than 3, the amplitude is decreasing. So near 3, there is a kind of resonance or a large, yes, a large increase in the amplitude of the system, right? This is known as the resonance. So you get the three kind of systems, right? Or is there any doubt? Okay, then. Manoj, right. These are the three cases: the simple harmonic case, the damped harmonic case, and the forced damped harmonic oscillator or the damped driven harmonic oscillator. You can also play with it if you have Wolfram player. There is an app or a software called Wolfram player. This one Wolfram player 2.2 I have. So if you have this, just you can ask me. I can send it to you. Then you can also play. Just download it, and you can also change the parameters to get what kind of plots get for different kind of parameters, right? So this is all about today, and tomorrow we will start the theory of determinants, sorry, the matrices and determinants. Then our course on mathematical physics will be over. The last remaining topic is matrices and determinants, and just one more class on the complex algebra. Then this course on mathematical physics will be over, right? Is it okay? Okay, okay, so then so that's it for today. So let's meet tomorrow. Good night. Good night.